That was sketching functions, and it says this one, f is positive. Now, what does that mean? That means the entire graph is above the x-axis. Because if it goes below the x-axis, the y values are negative, right? And the function value is negative. So if you want to keep your function positive, we want the graph to be above the x-axis. So I know when I'm sketching this graph, I will have to make sure to stay above this x-axis. Okay, now the second clue says f prime is negative. What does that mean? Well, that tells us that this function is decreasing, which means going down from left to right. Okay, and now the third clue. Now this one's a bit tricky. It says the second derivative is 0. Now let's think about this kind of backward, okay? What kind of function has second derivative 0? Okay, now remember, when we take derivative, we go down on exponent by 1 every time, right? So for a function to have a second derivative to be 0, I'm thinking the first derivative has to be just x plus something, right? Or just not even x, I'm sorry, a constant, just a number, right? A number. Because when you take the derivative of a number, wouldn't you get 0, right? And if I just use c to represent any number, but I can pick a number, like I can say c is, let's say 2, okay? Now, if the first derivative is 2, do you agree with me that if you take the derivative of 2, wouldn't that just be 0, right? But this doesn't have to be 2. This can be 2, 3, 4, 5, -1, -2. Any constant will have a derivative of 0. So I'm going backward, okay? I'm just thinking about some function. Now, what will be the original function if the first derivative is 2? Well, what if the original function was like 2x? You see, I'm kind of going backward, right? I'm taking the antiderivative, right? We'll do this in section unit 4, but for right now, I was just using the clue that if the second derivative is 0, the first derivative has to be a constant, which means the original function has to be a linear function. Now let's think about this though. Is this function decreasing? Is this function going down from left to right? Not really, right? If I keep it like this is actually going up from left to right. How can I make this going down from left to right? Well, I can just make the slope negative, right? So this is now going down from left to right. The derivative of -2x will be -2, and the derivative of -2 will be 0. So I think we found a function, okay? I will have to restrict this though, because this function will not stay above the x-axis for so long, right? Because this is going to go down below. So I may just have to just sketch a part of a graph, not the entire graph. But let's say that I have a y-axis like this, and I'll just sketch a function that looks like this, like a straight line going down, okay? But I'll just try to keep it above the x-axis, okay? Because if it goes below the x-axis, then it is not positive. So we will say, hey, I'm just going to make a piecewise function, a piece of a graph with some domain restriction, okay? But this function has to be above the x-axis to be positive, has to be going down, so that is first derivative is negative, but it has to be a straight line function, so that when you take the derivative twice, the second derivative comes out to be 0. So it shouldn't be a curvy function, it has to be a straight linear function whose exponent or degree is 1. so that when you keep on taking the derivative, the x completely just goes away. Okay, so that is how we can graph a sketch, and this is just an example. But let's try another one. Okay, what about this one? It says f is positive. Oh, same restriction, right? If f is positive, then we must be looking at a graph that is completely above the x-axis. Now it says f prime is 0. No, what does that mean? So it's not increasing or decreasing. You see, when they say f prime is 0, when f prime is 0, means, is it increasing or decreasing? No, it's not. It's not going up or it's not going down. Means the graph is constant. Graph is a flat line. Oh, I shouldn't say flat line. I'm sorry. I'll just call it as a horizontal line. It's not, I should say, it's not increasing or decreasing. So what kind of line is not going up from left to right? It's got to be a horizontal line. Now let's talk about the last part. That the second derivative is also 0. Okay? Well, we know what kind of function has a second derivative 0. A straight line function. A straight line function. So let me see. Let me think. But this line has to be a flat liner though. Okay, so I'm gonna just write an equation of a flat line function. What if f of x is something like 3? I just made one up. What if f of x is 3? Now I did it so that it is positive number, so that it's graphed above the x-axis. Let me see if this will work. Okay. So if I graph a function, 1, 2, 3. If I graph a function 3 above, say that's my function, okay? What happens if I take the first derivative of that function? Take the derivative of positive 3. That comes out to be 0, right? So that met the first condition, or actually the second condition, because the first derivative is 0. Now, what happens if I take the derivative of 0? Take that second derivative, it also comes out to be 0. So it met the third condition of second derivative being 0. So as long as you graph a horizontal line above the x-axis, it could be f of x equals 5, 6, 7, 8, negative. No, it cannot be negative there, right? Because to keep it above the x-axis, to make this function positive, we need to pick a number that is bigger than 0, okay? So that is it. I think that should be enough. I think I'm going to stop the recording. And you know what? I'll take care. I'll do this one too. So right below these sketching examples, we have an example reading graphs. Let's do this one. It says, given the graph below, find the intervals where f is concave down. Okay. Concave down looks like this. Okay. Concave up looks like this. I don't think I've actually told you why though. Let me use this chance to talk about why these are called concave up or concave down. Now imagine sketching a tangent line to this graph right here, to this blue graph. Okay, tangent line, that gray tangent line right there, right? Another tangent line right there, right? Another tangent line right there, and another tangent line right there. Notice all these gray tangent lines are above, making the graph to be below these tangent lines, right? So that's why we call this concave down. If the graph is below all these tangent lines, we call it concave down, okay? Now, if I try to sketch some tangent lines for this pink graph, notice the graph is above this tangent line, right? Notice this graph is above the tangent line. And again, the graph is above the tangent line. So when the graph sits above the tangent line, we say this is concave up. Okay? All right, let me erase some of. Oh, whoopsie, I want to erase my graphs. All right, you ready to read the intervals of concave up and down on this? And they want the point of inflection where the concavity changes. So let's see. Take a look at this for me. I think I noticed it. So this right there is definitely concave down. And I think it switches concavity at this point right there. Because to the right of that point, we definitely have a concave up graph. Okay, so the point of inflection looks like it's right at oopsie, hold on. 1, 2, 3, 4. So the point of inflection is at 4. Now, it's down 1, right? The y value is -1. The POI at 4, -1. This graph is concave down on -infinity to 4 and concave up on 4 to positive infinity. So, I don't know, it may be kind of confusing or challenging to see where that change happens. I wonder if there's like a trick to see that point of inflection. But point of inflection is where the graph really just changes the concavity. So if I try to maybe add some tangent lines, so definitely the graph is definitely below, right? But this is where the tangent line will switch the behavior. Okay, but try the homework problems and see if you have like other questions that may be a little different than this or confusing, and you can always email me about them. But in this video we sketched 2 functions to meet the descriptions, and one example where we were reading graph and finding intervals where it was concave down or up and the point of inflection.